At 828 meters tall, the Burj Khalifa rises into a sky that regularly delivers wind speeds capable of snapping steel cables and sandstorms that reduce visibility to near zero. The Arabian Gulf sits just a few kilometers to the east. The desert stretches in every direction. And yet this tower, the tallest structure ever built by human hands, stands without swaying into catastrophic resonance. The reason has almost nothing to do with brute strength and everything to do with shape. When Skidmore, Owings and Merrill won the commission to design what would become the world's tallest building, the engineering team, led by structural partner William F. Baker, faced a problem that no one had solved at this scale before. A super-tall tower in a desert environment doesn't just face ordinary wind loads. It faces a specific aerodynamic threat called vortex shedding, and at 828 meters, the consequences of getting it wrong are not cosmetic, they are structural. Here is what vortex shedding actually means. When wind hits a blunt or cylindrical surface, it separates on either side and forms spinning columns of air, called vortices, that peel off alternately from each side of the structure. Those vortices don't just push the building, they pull it rhythmically from side to side. If the frequency of that pulling matches the building's natural sway frequency, the structure enters resonance. The oscillations amplify. In the worst cases, the building can tear itself apart. This is not a theoretical concern. It has destroyed bridges. It has collapsed chimneys. At the height of the Burj Khalifa, the forces involved are enormous. The conventional engineering response to this problem is to make a building stiffer, heavier, or to add damping systems that absorb the energy of oscillation. Many super-tall towers use tuned mass dampers, essentially giant pendulums or sliding weights near the top of the structure that swing in opposition to the building's movement. Taipei 101, which held the world height record before the Burj Khalifa topped out in 2009, uses a 660 metric ton steel pendulum for exactly this purpose. Baker and his team considered the full range of options. What they arrived at was more elegant and more fundamental. The solution was to confuse the wind. The Burj Khalifa's cross-section is not a simple circle or square. It is a Y-shaped tripartite form, with three lobed wings arranged around a central core. As the tower rises, each wing steps back at different heights, so the building's profile changes continuously as you move upward. The result is that at any given elevation, the building presents a different width and geometry to the wind than it does 50 meters above or below. This is not an aesthetic choice, though it produces a striking silhouette. It is a deliberate aerodynamic strategy. What the setbacks accomplish is this. They prevent vortices from organizing along the full height of the tower. For vortex shedding to become dangerous, the spinning columns of air need to form coherently across a large span of the structure, building up synchronized force. When the building's shape changes at each setback, the vortices that form at one level are out of phase with those forming above and below. They cannot lock together. The resonant frequency that would drive catastrophic oscillation never fully develops. The wind, in effect, cannot find a consistent surface to push against in a coordinated way. This approach required extensive wind tunnel testing. Scale models of the tower were subjected to simulated wind conditions from multiple directions, because in a real urban environment, wind does not arrive from a single angle. The testing informed not just the final shape, but the precise heights at which each setback occurs. Every step in the tower's profile was a calculated intervention in the aerodynamic behavior of the structure. The Y-shaped plan also distributes the building's mass efficiently. Each of the three wings acts as a buttress for the central core, and the core stiffens the wings. This bundled structural system means the tower resists lateral loads, whether from wind or seismic activity, through the geometry of its own form rather than through sheer material mass. Using less concrete and steel to achieve the same structural performance was not just an engineering preference. At this scale, it was a practical necessity. The logistics of constructing the world's tallest building in the middle of a desert, with summer temperatures exceeding 45 degrees Celsius, meant that every unnecessary kilogram of material represented a compounding cost in time, labor, and supply chain complexity. There are aspects of the Burj Khalifa's performance that remain subjects of ongoing study rather than settled engineering consensus. The long-term behavior of super-tall structures under repeated wind loading, thermal cycling in extreme desert heat, and the interaction between the tower and the urban microclimate it has helped create around downtown Dubai are areas where observational data continues to accumulate. The building is instrumented with sensors that monitor structural movement and environmental conditions, and that data informs both the management of the building and the broader field of super-tall design. What engineers know from direct measurement is that the tower performs within its design parameters. What the full picture of its multi-decade behavior will look like is still being written. The Burj Khalifa topped out in 2009 and has held the title of world's tallest structure since then, surpassing Taipei 101, which had held the record since 2004. As of mid-2026, the Jeddah Tower in Saudi Arabia, designed to reach at least 1 kilometer in height and stand at least 180 meters taller than the Burj Khalifa, has surpassed its 106th floor and continues to rise. The aerodynamic principles that Baker's team refined in Dubai are not being discarded for that project. They are being extended. The problem of vortex shedding does not get easier as buildings get taller. It gets harder because the wind loads increase, the resonant frequencies shift, and the margin for error narrows. What the Burj Khalifa actually demonstrated is that the most powerful engineering interventions are often the ones that work with physical forces rather than against them. The tower does not overpower the wind. It denies the wind the coherent surface it needs to organize a destructive response. The shape is the structure, and the structure is the solution. That principle, refined in the desert heat of Dubai, is now the baseline assumption for every super-tall project that follows. The next question the field is working to answer is whether the same logic scales cleanly to a kilometer and beyond, or whether that threshold introduces aerodynamic behaviors that a stepped Y plan alone cannot fully address. The Jeddah Tower will be the first real-world test of that question at full scale. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.